I just wanted to take a couple of minutes and talk to y'all about signal and noise. So this is a unique problem to instrumental analysis that we have to deal with electrical noise, and probably have not had to think very much about it from a theoretical standpoint. And so that's today's goal. So today we're going to define signal and noise, and we're going to think about the different categories of noise and how to quantify noise in chemical measurements. So before we get going, I want to ask you to stop the video and sort of brainstorm what you think signal and noise really mean. So take notes on your own for just a minute. All right, so maybe what you came up with is something like, if I were going to draw a thought bubble, maybe some words that you came up with for noise would be something like random. Sometimes it's random. Maybe time dependent. Might be errant signal. Might be something about a mean signal or a standard deviation from that mean signal. These sorts of things, right? In fact, noise is random, or usually random. Time dependent. Changes in instrument output. Signal that is unrelated to an analyte response. Which once I read it probably makes some sense, right? We should probably talk about what analyte response actually is then, right? So that's what we define as signal. So a signal, an actual signal, carries information of interest to a scientist about a chemical system. So for example, information could include things like bond lengths, positionality of atoms in a particular molecule, something relating to quantity of molecule or atom, those sorts of things, right? So if we want to define signal and noise, we've done so, and hopefully those two definitions sort of make sense. We'll use those as we move forward and continue our discussion. The next thing I want to talk about is how we really quantify noise in the laboratory. So it's true that noise is inherent to all chemical measurements that we make, especially those using instrumentation that contains electronics. But the magnitude, frequency, and source can be unique depending on the measurement being made. So the magnitude, frequency, or source can be unique. And so we're going to talk a lot about that in the upcoming slides. But before we get there, let's talk a little bit about noise in general and how we measure it or quantify it in the lab. All right, so the average strength of noise, which we're going to give the variable capital N, is constant and independent of the magnitude of the signal S for a particular measurement. Thus, the effective noise on relative error becomes greater and greater as the magnitude of that measurement decreases. So this really becomes an issue. Noise really becomes an issue when you start talking about trace analyses, right? And trace analyses being a pretty big part of the field of modern analytical chemistry or quantitative analysis using instrumentation. Noise is always something that we are contending with in the lab. So we characterize noise using a signal to noise ratio. So that's this ratio right here, signal to noise. And we can actually put a number on it, right? Or make a ratio by taking the mean of a particular measurement and dividing by the standard deviation. That ratio that results is what we like to call signal to noise. And so in general, it becomes hard to detect a signal when the signal to noise ratio is less than 2 or 3. Okay. So an example over here on the right, in panel A, I have a relatively noisy signal. In panel B, it's smoothed out. What we're talking about with noise is really this deviation from the average, right? So if I were gonna, before I say that, notice that if I were gonna say, this is the smoothed version, right, of panel A, I could sort of draw that in and it would look the same, okay? Maybe a little bit down here, okay? So really what we're talking about when we're talking about noise is this deviation from a mean, which makes sense, right? We're talking about a standard deviation from a mean. So here I could look at this, I could try to calculate a standard deviation. My signal is, the mean signal is at about 1, right, on the y-axis here, and my deviation is about 0.5, right? So this figure would represent a signal to noise ratio of about 2, just sort of estimation. And you can see that that signal really does become hard to see through the random deviation of the noise across time. So let's talk a little bit about how we define how we can quantitatively define noise. So the way that I've just done it using the top and bottom sort of range around a mean is called peak to peak noise. So we call it N sub PP. So this is a range, right, like I just said, or a difference between the maximum and minimum values of discrete signal measurements over a defined amount of time. Okay. So I could say my defined amount of time was just this long. What would that be? Maybe like 0.4 seconds, or sorry, no, that's in unit of hours. So maybe 20 minutes, something like that. 25 minutes. This range could also change, right? If I made this range much longer, okay, in fact, this average would probably go down a little bit, right? If I'm making it much longer, the average top peak noise would probably be something like this. And so that changes the range of noise, right? So it's the reason that this is important to think about is because this is peak to peak noise over a defined amount of time. Okay. And you can make that definition and of what you can choose that length of time over which you'd like to average the peak in noise, but you have to tell, to report out what it was. Okay. And hopefully it makes sense for the magnitude of the measurement that you're making. Okay, I digress. So the other option is, one other thought is average noise. So interestingly, if noise were truly random, average noise would be, right, 0, because you'd have an equal amount of deviations from in the positive direction and an equal amount of deviation in the negative direction. So if noise isn't 0, and usually it's not, then there must be some other signal present that isn't accounted for. And so this average noise is really sort of a useless way to think about it, but you might hear people who aren't in the know talk about average noise. All right, so the last one is really the most useful way to quantify noise, and we call it root mean squared noise. So this is a measure of the instantaneous deviations from average to 0 over a long period of time. And this is nice because it gives a more accurate description of noise. It also is kind of useful in that it quantifies noise in both directions into one sort of measurement that's more accurate. Okay, so the way that we talk about this is we talk about it as S sub E being equal to the sum of the instantaneous deviations minus the average change. Okay. We square that sum, divide by n minus 1, so n being the number of measurements. Oh, sorry, this should be a small n. and then take the square root. And so really what we're doing is maintaining magnitude while getting rid of any sign effect in this calculation. So root mean squared. So root mean squared noise is the way that we'll hopefully try to quantify noise throughout the rest of this class. Sometimes it's hard to calculate root mean squared noise, mostly because you need to know an average error and you need to know something about the instantaneous deviation. So like actually using this equation can sometimes be difficult given the kind of data you actually have. And so one way that we can get to it in a roundabout way is to calculate it using NPP noise. So if we treat noise as a statistically random deviation, oops, no, that's not the right button. Statistically random deviation from an average, right? As if measurements would fall into a normally distributed fashion, right? So I've got a normal Gaussian distribution pictured here on the right. So at plus or minus 2.5 sigma, right, 2.5 standard deviations away from the mean, at that spot, you're talking about 99% of the area under that Gaussian curve. 99% of the area under the curve. So taking this into account, we say that the range of signal that falls plus or minus 2.5 standard deviations from the mean is actually equal to 5 sigma, right? And so therefore 5 sigma is equal to NPP for random noise. Okay. Meaning, if we know that, one thing I forgot to mention, I apologize. RMS noise also equivalent to standard deviation. So it's hard to calculate theoretically. This is what we measure most often is random root mean squared noise. If you can't measure it, you can, or if you don't have the like numerical data in front of you to do the calculation for standard deviation, you can estimate it using NPP, which is what we're trying to talk about here. So if you have 5 sigma equal to NPP, because we know that the root mean squared noise is equal to 1 standard deviation, that means that 1/5 times times peak to peak noise is equal to root mean squared noise. Okay. What does that really mean? I know that doesn't help you, but I'm turning my iPad right now, okay? And if here's my average signal, right? That means that all of the deviations that we're going to see in that signal, okay, 95% of them, right? Or sorry, 99% of them, that's where we are, 2.5 standard deviations away, are going to fall in plus or minus 2.5 standard deviations from the mean. So that's this direction, 2.5 standard deviation away, and this direction, 2.5 standard deviation away. So there's some that we're not catching, and that's okay, right? But there are some, in fact, most, 99%, that are going to be included in this 2.5 or 5 sigma, 5 standard deviation range. Okay, so that's what we're trying to estimate with this root mean squared estimation from peak to peak noise. Okay. All right. So here's what I'd like you to try. I'd like you to try calculating what is the signal to noise ratio in the spectrum below. And certainly you have a couple of options here. Because you don't have any numerical data, root mean squared noise is going to be hard to calculate. And so maybe the best bet would be to estimate NPP noise. And then what I'd like for you to do is report out RMS noise given that NPP estimation. Okay, so pause the video, work on this on your own, and we'll reconvene. All right, so one question I have for you as you did this is to wonder, did you measure signal from a theoretical zero, like somewhere down here on the y-axis, or did you subtract some sort of baseline? And so for me, I subtracted baseline. So I said that the top signal here was at 3000, but base signal here was at 750, right? So this gives an answer of 2250 for the adjusted or baseline subtracted signal. I said that that noise, which I characterized from here to here, although it would have been valid to do sort of any spot on this spectra that has that random variation. I said noise, NPP noise specifically, estimated at 1,000. For that range was about 1,000. And so I took off 550 to give 450 as my total. Okay. Now I found root mean squared noise by taking 1/5 of that 450 value for peak to peak noise to give a root mean squared noise of 25. Pretty fun stuff. All right, so I would like for you to try a couple more of these problems on your own, and I'll post the answer key up on Brightspace. All right, so if it's not obvious, this is a link to a new Google Doc that has, or to a new PDF that has a couple more problems in it. So go ahead and try that out. All right, so now we've talked a little bit about how to calculate noise and what signal to noise ratios are appropriate for instrumental analysis purposes. But now let's talk about sort of where it comes from and what we can do about it. Well, we'll talk about what we can do about it in the next video, but a couple of ways that we characterize noise. We can give it two labels, basically. Every kind of noise can get two labels. It can either have a random or non-random direction. Okay, so direction is one way that we characterize noise. The other is source. Okay, so if you have a direction that's random, that means the sign and magnitude of those instantaneous levels away from the mean are unpredictable and irreproducible. Okay. If it's non-random, you have a sign and magnitude of instantaneous levels that can be correlated to some sort of event. Okay. For source, if it's fundamental, it arises from the particle nature, physical nature of light and matter and can't be eliminated. You just kind of got to live with it. And it's just a balance of signal to noise. If it's non-fundamental, it's due to imperfect components in an instrument and theoretically could be eliminated. So this is the spot where we're going to sort of live for the next few slides, is talking about non-fundamental source noise, which may or may not be random or non-random. All right, so there are three main sources of noise. You're almost always dealing with at least two, and depending on what your the system you're measuring something in, you might have a third. So the first is chemical noise. So this arises from a host of uncontrollable variables that affect the chemistry of the system that's under analysis. I give some examples here of temperature, pressure changes, humidity, etc. Another thing that might come up is if you have a not well-defined chemical equilibria, that some equilibria that are shifting, that would arise or give rise to some chemical noise in your measurements. The next is instrumental noise. So this is the noise that's associated with each component of an instrument, things like input transducers, all signal to processing elements, output transducers. So unfortunately, because there are so many bits that go into producing noise in an instrument, it's really hard to deconvolute their source. And some types of instrument noise can be eliminated, but some just are really hard to identify and get rid of. But this is where we're going to live. We're going to try to figure out how we can get rid of some of those pieces of instrumental noise. The last kind of noise that you might want to consider, depending on the system that you're making measurements of, is biological noise. So here, thinking about measuring something in a cell or within an animal or in any sort of biological system. Biological systems are intrinsically heterogeneous, right? They fall prey to stochastic fluctuations of molecular processes, things like translating RNA to protein, things like the degradation, like random degradation of proteins, nucleic acids, that sort of thing. And the quantification, the quantitative, distribution of such fluctuations is called biological noise. Okay. All right, y'all. So we're going to sort of live in this area. So we're going to talk about non-fundamental instrument noise moving forward, which may or may not be random. All right, so if I'm going to start to classify instrumental noise, there are two kinds of white noise that we're going to talk about. The first is called thermal or Johnson-Nyquist noise. And so thermal or Johnson-Nyquist noise comes from random variation of electron motion in a solid. All right, so let's write this down. Rises from random variation in electron motion in a solid. It's always present, even in the absence of any sort of resistive elements in terms of like electronics. And it only disappears when you're at absolute zero. So this random movement periodically creates charge inhomogeneity, which in turn makes voltage or current fluctuate. Okay. We can calculate thermal or Johnson-Nyquist noise using the equation to the right. So VRMS, so the noise is root mean squared noise that has a thermal origin. And the equation is the square root of 4K, where K is Boltzmann's constant, T is temperature in Kelvin, R is any sort of resistance in the system, not necessarily from a resistive element, but just of the system that's sort of inherent to it. And then the delta F is bandwidth. So we should probably define bandwidth. So bandwidth, as defined in this equation, is equal to 1 over the rise time, 1 over 3 times the rise time of the system. Okay, so as noted here, the rise time of an instrument is defined as its response time in the unit of seconds to an abrupt change in an input. So after, let's say, a photon hits a detector, how long does it take for that detector to say, hey, wait, I've been hit. Now I must give output signal. Okay, so that rise time, and it's normally defined as the time required for the output to increase from 10% of the total value to 90% of its final value. Okay. So, for example, if I have a rise time of 0.1 seconds, that means that my bandwidth is 3.3 hertz, right? I'm talking about per second here. All right, so ways that we can decrease thermal noise. We can narrow or decrease the bandwidth. Because there is an inverse relationship on rise time, between rise time and bandwidth, what this really means is you're increasing the length of a measurement, the amount of time it takes to take measurement. And this results in less sensitive measurements. Okay. In an electronic instrument, this usually can be done using electronic filters. The second thing you can do is to lower resistance. Right? That makes plenty of sense, except it's kind of hard to do because usually what that means is you're changing materials, using a less resistive material in your system. The other thing you can do, which is more common but very expensive, is to lower the temperature of your system. So in really high-end detectors, for example, you might have liquid nitrogen or helium-cooled detectors. Okay. This is common in high-end NMR, FTICR, mass specs, and ICP OESs. Okay, the next kind of instrumental white noise is called shot noise. Shot noise comes about when electrons or other charged particles cross a junction. And remember, noise happens in the absence of any chemical reason or characters, any sort of reason that characterizes the chemical system. So it's not supposed to be happening, but it does, right? So when we have charged particles crossing a junction when they're not supposed to. If you want to draw like the classic photocathode, maybe it looks something like this. I'm not an artist, excuse my skills. So here's my glass dome. Here's my cathode and anode, right? And what happens is I have a photon that comes in and hits my hits one of my electrodes here, and that electron is going to jump right to the cathode across this gap. And of course, the atmosphere under this glass dome is held at vacuum, so it's making that jump without any sort of conductive material. And so currents, right, comprise a series of quantized events and the transfer of individual electrons across the junction. These events occur randomly and are described by the following equation. So I've got current, right, root mean squared noise equal to the square root of 2 times the charge multiplied by the direct current multiplied by bandwidth. So don't think about B, think about delta F, same delta F from before. And so the other question I'm going to have for you then is, how do we minimize shot noise? And again, we can decrease the bandwidth, which decreases the sensitivity of our measurements. We can decrease the current in this case. Again, what we're doing is minimizing the signal intensity that results, and so we're minimizing sensitivity. And then really the way that this shakes out in real life is it's really impossible to get rid of shot noise. And so it's a balance of decreasing bandwidth and current, but making them be high enough that you can actually get a signal above noise, right? So this is just always a balance in the actual laboratory. All right, the next kind of noise I want to talk about after white noise and its two subcategories is flicker or pink noise. So this kind of noise is inversely proportional to the frequency of the signal being observed, right? So if you have a high frequency signal, you'll observe this this noise in the low frequency range. Its origins are uncertain. We don't know why this happens, but it's characterized by that inverse dependence on the measured frequency. It's observed as long-term drift in signal. And you can see it in light sources, power supplies, voltmeters, that sort of thing. And really it's only significant at frequencies lower than 1 kilohertz. All right, this is another kind of noise that we just kind of have to live with and deal with. The last kind of noise that I want to talk about is instrumental noise that arises from the environment. Another kind of noise that we really can't get away from, right? Environmental noise is a composite of different forms of noise that arise from wherever the instrument is. So each conductor in an instrument is potentially an antenna capable of picking up electromagnetic radiation and converting it to an electrical signal. So I call this a noise power spectrum. Noise power spectrum. So places we have to watch out for in particular, and instrument manufacturers do, is sort of this area right here, where most of our normal power frequencies are. So you might see power cycle changes in the year, right? Sort of frequency, day, hour, minute. But as you keep increasing and going to the right, you see ones that are more relevant for changes in signal arising from instrumental measurements. So it's sort of an anecdotal story. When I was a graduate student at the University of Minnesota, I did a little bit of work in a spectroscopy lab. And at the same time that we were trying to make some pretty sensitive measurements on our laser table, the University of Minnesota system was having the light rail above ground electric train system construction happened through the U of M campus, and it went right next to our building. And so we actually had to increase if you've ever seen a laser table in a lab, it's actually on like pillows that are filled with air or springs to sort of minimize the vibrations that happen like in the building, to minimize that noise that you might find in your spectroscopic measurements. Anyway, we had to put in extra springs and airbags on our laser table to minimize the effect of the vibrations from the train that was going right next to our building, which is kind of like a real world concrete example of why environmental noise is sometimes hard to identify, but hopefully easy to remedy. All right. So I'm going to leave it here for you. I will see you in the next video where we talk about how we can actually try to attenuate some of the noise that we might be dealing with in the lab.